Good morning, ladies and gentlemen. Firstly, thank you all for coming along this morning to listen. I'm very pleased to see that there are so many people who are interested in fusion. What we're trying to do is to explain things in a fairly straightforward and simple manner, so that we don't talk over people's heads and so that people can go away with a message. I hope that you'll be able to go away from this seminar understanding why we're doing fusion, what fusion is, what a plasma is, and indeed what a tokamak is, what ITER is. So, let me start with the bad news. You've probably all heard that a really good talk leaves you with a single simple message. Now, unfortunately, I've got 5 messages I want to give you this morning. I wanted to begin by explaining to you very briefly why we're doing fusion research. We're spending a lot of money. We're going to spend nominally 5 billion euros in ITER. And there has to be a better justification than it's just a bunch of physicists who need something interesting to do. And then I'm going to explain what fusion energy is. Where do we get fusion energy from? That leads me on to an issue which you've probably all heard the word plasma. And I'm going to explain why we're involved with plasmas, what a plasma is. And I'm going to explain how we hold the plasma together. How do we confine is the technical word we use, meaning just how do we hold the plasma together? Why we want to hold the plasma together. And then that'll lead me to the final subject, which is a little more complex. And that is, what is a tokamak? Why are we doing fusion research? You need to think about energy. And you need to think about our needs for energy. Not just energy now, but energy in the future. And so if you ask yourself, where does the energy we use now come from? You find numbers like this. 37% of our energy comes from oil. 21% comes from gas. Nearly 22% from coal. So we're up to 80% of our energy needs already. It's all fossil fuels. All sources of CO2 production, greenhouse gases. If you ask where the rest comes from, 6% comes from fission. Now in France we're luckier because more like 70% comes from fission. But globally it's only 6%. 6% comes from hydropower and 6% comes from what's called traditional sources. Basically burning wood. It's basically more fossil fuel. You're up to less than 1% before you start looking at the renewable sources. By renewables we mean all the things that people talk about these days. Wind power, solar power, geothermal, biomass. At the moment it's a very small fraction of our energy production. Most of our energy comes from fossil fuels. Most of our energy is a potential source of greenhouse gases. That's the first problem we face. The second problem we face is, if you look at what's going to happen to the world's population in the future, and what's going to happen to the energy requirements, the expectations are that they're going to increase fairly rapidly. We're here just after, we're in nearly 2010 now, we have a population of just over 6 billion in the world, and predictions suggest that by the end of the century that's going to be in the region of 10 to 12 billion. Our energy needs are going to grow similarly. Now it depends, of course, predicting the future is always very difficult. As you can appreciate if you have any investments in the stock market. There are different growth predictions depending on how rapidly you assume the world's economy will grow. But at least on the most pessimistic prediction, we expect that energy usage is going to double over the next century. More optimistic projections it could increase by a factor of 4. And most of this increase is not going to come from Europe, the US, Japan, Korea, the developed economies. Most of this increase is going to come from countries such as China and India, which are developing economies with large populations, and it's their aim to bring their population standard of living up to the standard of living in the West. And that means their energy usage will come up to the standard, the same level as in the West. And the problem is that, as I said, fossil fuels provide at least 80% of our energy needs today. But the resources are finite. We are already predicting that we're very close to the peak production of oil. And increasing energy consumption through fossil fuel will increase fossil fuel consumption, will increase CO2 production, and may well cause climate change. so you then ask, what are the medium and long-term options? Well, we think, obviously, that fossil fuel is not really a medium and long-term option. We have to reduce our dependence on fossil fuel. And so that only leaves three general sources. Renewables, as I said, solar, wind, and so on, that'll have to grow in the future. There's no question of that. Nuclear fission, which is not really regarded as politically acceptable now, but it's one of our few future sources of energy, and it will probably grow again. There's already evidence that the world is turning back to nuclear fission. And then there's fusion, the technologies that we're working on. So this is why fusion research is so important. There aren't many options for our energy in the future. Fusion is one of those. That's why we need to exploit it. Why is fusion such a potentially important source of energy? Well, firstly, there's an awful lot of fuel about. I'm jumping a little bit ahead here. I'll explain later that the basic fuels for fusion are gases that are called deuterium and tritium. And their basic source fuels are very abundant and they're distributed worldwide. There's sufficient deuterium in seawater for our energy needs for millions of years. As far as we're concerned, it's inexhaustible. Tritium is another gas which is produced from neutron reactions with lithium. I don't have time to explain this today, it's another lecture. But tritium we can get readily, easily from lithium. And conservative lithium ore recovery estimates indicate that sufficient supplies for thousands of years. So it's the ores on land are sufficient for our energy needs for thousands of years. We can also extract lithium from seawater, and the resources there are sufficient for millions of years. So this is a big thing. This is an essentially inexhaustible supply of energy, if we can make it work. Safety, and this of course is very important. In fusion, we believe there is no risk of a major accident. Fundamentally because the reactor contains only enough fuel for a few seconds of burn. One of the very interesting things about a fusion reactor, you have to keep putting the fuel in from the outside. If anything goes wrong, there's only enough fuel in there to keep the burn going, keep the fusion energy going for a few seconds. So you're not going to get a meltdown. In relation to waste, radioactive waste, we will produce radioactive waste because, as I'll say, we produce neutrons in fusion reactions. They combine with the materials in the walls of the reactor, and they produce radioactive elements. But we're working on special materials, what we call low activation materials, that will produce radioactive isotopes, which decay very rapidly. And it's our aim to produce materials that would allow us to basically dispose of the material relatively easily after about 100 years after the reactor stops operating. So there isn't going to be radioactive waste which is going to last for thousands or even hundreds of thousands of years. Work has been going on these materials for about over 20 or 30 years. There's been a lot of progress in this area. It's our intention that the next generation of devices that come after ITER should be built from these low activation materials. So these are basically the elements of the fusion story that make fusion such an attractive potential source of energy. So I talked all about why fusion is so attractive. I should explain what fusion is. Basic principle is very simple. It's illustrated here. You take two atomic nuclei, which are positively charged. You force them together to fuse. You produce a large atomic nucleus with some energy left over. And I'll explain where that energy comes from in a moment. But this already illustrates one of the problems about making fusion happen. And it's why, one of the reasons it's taken us so long to get to where we want to be. And that is, these are positively charged nuclei, and you know that positive charges repel each other. So if you try to bring these nuclei up together quite gently, they just bounce off each other. And even if you try to fire them against each other, they bounce off each other. You're really going to smash them together to get them to fuse and produce energy. And it's getting them to smash together with enough energy that it's caused us all the difficulties in fusion research over the years. Because it's figuring out how you do that effectively and efficiently. Because of course, if you're going to take energy to smash the nuclei together, to fuse them But there are two heavier isotopes of hydrogen. One of them is this material called deuterium that I referred to previously. And this is just a hydrogen nucleus in which we've added a neutron. So it's twice as heavy as hydrogen, but it's still hydrogen because the chemical characteristics are determined by the number of protons and electrons you have. So this is heavy hydrogen. And then there's a third isotope called tritium, in which you add two neutrons to the nucleus. And it's these two heavy isotopes of hydrogen that we can fuse together. And we use these two heavy isotopes. I mean, this is much more abundant. You might say, why not just use ordinary hydrogen? Well, it turns out that the reactions between these two go much more rapidly than the reactions between hydrogen and hydrogen. So these two are much easier to get to fuse together than if you use normal hydrogen. And so these, the isotopes of hydrogen, deuterium and tritium, is the fuel that we use in our experiment here on Earth. So, how do we get the energy out of the fusion? Well, the basic principle is very simple. I think you've all heard of Einstein's famous equation, E equals mc squared. It basically says that there's a relationship between matter, and energy. And the constant of the relationship is the speed of light squared. So basically, if you can take some mass and convert it entirely to energy, the multiplication factor is the speed of light squared. And that means that any mass contains a huge amount of energy. A gram of any material contains an energy equivalent to 10,000 tons of TNT if you could convert it to energy. So this is a very effective way of getting energy out of matter. So, what is it we actually have to do? Well, this is the basic scheme of the reaction. You start off with tritium and deuterium, and you fire them against each other. And you produce, for a very fleeting instant, a heavy nucleus, which is unstable. And this nucleus breaks up into helium, and the helium whizzes off with 20% of the energy of the reaction, and a neutron, which takes 80% of the energy. Now the key thing is, if you collect all, if you were to measure or weigh all of the tritium and deuterium you put into the reactor, collect up all the helium and neutrons that you produce in the reactor, you would find that the original mass of the deuterium and tritium is heavier than the mass of the helium and neutrons. It's a very small difference. If you had started with a gram of deuterium and tritium, you would find that only 4 milligrams disappeared. 4 parts in 1,000. Nevertheless, that would give you the energy equivalent of 2,000 gallons of oil. So a gram of deuterium and tritium, if fused together, produce enough energy to replace 2,000 gallons of oil. And this is also why fusion is such an attractive source of energy. So that's the basic principle. You're just taking matter, you're combining it together into a different form of matter. There's a very small mass difference between what goes in and what comes out, which is converted entirely to energy. And it's a very efficient source of energy. And so the next thing I want to talk about is what is a plasma. Because that's important to understanding what we're trying to do here in ITER. Plasma is generally referred to as the fourth state of matter. And the sequence looks something like this. Let's consider water. It's very simple. If you have water below 0 degrees Celsius, you have a solid. You have a crystalline structure, you have ice. If you warm it up above 0 degrees C, you get a liquid, what we call water. If you heat it beyond 100 degrees C, you get a gas, what we call steam. If you heat it even further, up to around 10,000 degrees C, what starts to happen is quite interesting. Because when a gas gets hot, the particles are whizzing around, they collide with each other. Now most of the time in the air they just bounce off each other. But when the energy of the interactions gets high enough, when you get the gas hot enough, the collisions are powerful enough that the electrons and the nuclei are broken apart. And so what starts to happen is instead of having a normal gas what you actually have then is this fourth state of matter. It's a mixture of ions and electrons in which the ions and electrons are flowing around separately inside the plasma. So it's a mixture of electrically charged particles. And this is going to be important. In the plasma, the particles, the individual particles are charged. In the air, the particles are neutral. So that's an important thing to remember. Another important thing to remember is, clearly, we're talking here about 10,000 degrees. You have a plasma at around 10,000 degrees. I told you before the temperature of the sun was 15 million degrees. So clearly, to get fusion reactions, we're going to need to produce a plasma. So that's why we call ourselves plasma physicists. And there are plasmas around us, even on Earth. I mean, I said the sun and the stars are plasmas, but you can see sites like this in the aurora borealis. And the aurora borealis is a plasma. It's particles from the solar wind trapped in a magnetic field around the Earth, causing the molecules in the Earth to radiate. In fact, more than 99% of the conventional matter in the universe is in the plasma state. So, to get fusion, we have to deal with plasmas. And if we're going to have to deal with plasmas, we're going to have to figure out how to hold them together to get the fusion reactions to occur. And so the question we then have to ask ourselves is, how do we confine a plasma? Well, the sun does it very easily. The sun uses what's called gravitational confinement. The sun is so massive that the gravitational attraction between the particles is so intense that it can hold the material together at these very high temperatures of 15 million degrees. But as you can see from a comparison of the Earth to the sun, this isn't really going to be a practical way of confining a plasma here on Earth. So we're going to have to find another way of doing it. And what you see here is actually a hint of what we're going to try and do. Because what's going on here in this prominence, this solar prominence, this is a blow-up of this region here. There's a very bright prominence. What's going on here is what's called magnetic confinement. Inside this bright flare, which is erupting from the sun, is a magnetic field. And the magnetic field is confining the plasma particles in this shape. Which, for those who are in the know, looks a bit like a torus, it's like a toroidal plasma. So, what is magnetic confinement? Well, let's sort of work our way through. Imagine we've got a sophisticated microwave oven. We've got hydrogen gas inside the microwave oven. So we're firing microwaves into this gas. Keep firing the microwaves in, the hydrogen atoms absorb the power, and eventually they get up to a temperature of around 10,000 degrees, and they become a plasma. We separate out the electrons and the ions in this microwave oven. We keep heating it, plasma gets hotter, or maybe it gets hotter, but of course the trouble is, just as the air molecules in the room are colliding with the walls of the room, so the particles in this plasma are going to collide with the walls of the oven. So in fact, they're going to collide, they're going to lose energy, you're actually not going to get the plasma very hot. So you have to do better than that. And this is where the idea of charged particles comes in, or the idea of magnetic confinement comes in. There's an interesting interaction between a charged particle, like an electron or an ion, and a magnetic field. Normally, ions and electrons will just whiz about randomly. But if you establish a magnetic field, what then happens is that the ions and electrons have to spiral around the magnetic field. It's the effect of the magnetic force on the ions and the electrons. And so then, instead of whizzing off and hitting the walls of the vessel, they start spiraling around the magnetic field line. And they don't hit the walls of the vessel anymore. So that's a step forward, or at least not many of them hit the walls of the vessel. There's still a problem, of course. Any finite oven with a magnetic field down the end is going to have ends. And these particles spiraling down the oven are going to spiral out the end and hit whatever is on the end. So that still isn't going to work. So the obvious thing to do if you want to stop things coming out the end is to bend it around in the form of torus, donut shape. So now the particles spiral around around the torus continuously. So the magnetic field stops them diffusing across and hitting the walls. And the fact that you have a torus means that they're just going around in circles. And now this is starting to look like what we call a tokamak. What ITER is. And this is the basic principle of what we're doing here. We're heating a gas up till it gets hot enough to become a plasma inside a toroidal chamber in which we have a strong magnetic field. And this strong magnetic field helps us to insulate the particles from the walls. There is still some collision with the walls, but it insulates it well enough. And the fact that it's a torus means that the particles just spiral round and round. And that's the basic principle of confinement, of magnetic confinement, that we use in a machine like ITER. So, I said this looks a bit like a tokamak, so I should explain very briefly what a tokamak is. The basic principle of toroidal magnetic confinement. This is a bit of a torus map. I've just taken a bit of a donut map. Schematically, we show the magnetic field lines going around. These lines, these black lines, are meant to give an idea of the magnetic field lines going around. And as I said, then the electrons and the ions are spiraling around the field lines. So basically, the fact that we've got this magnetic field and the particles spiral around it means that the losses to the walls now, the side walls of the chamber, are much, much slower than they would be without the magnetic field. And there's a very special version of this toroidal confinement system, this torus, which is called the Tokamak. And the Tokamak is actually a Russian acronym, which means toroidal chamber and magnetic coil. So, Tokamak. And the thing that's special about it is the precise shape of the magnetic field. As I said to you, what we need to do is to put this magnetic field around the torus so that the particles spiral around and around. Unfortunately, it turned out to be a little more complicated than that. Just having this simple field going around the torus doesn't satisfy all the requirements of physics. So a tokamak is a slightly more complicated version of this donut. What you see here is a schematic. These structures here are what we call toroidal magnetic field coils. They provide, they have currents flowing in them, and they provide this strong field going around the torus that I was talking about, the toroidal field. Now in ITER there are 18 of these coils. We produce with that a very strong magnetic field. Because a toroidal current will flow in the plasma. Because the particles of the plasma are charged, they will carry a current. And if we can apply an electric field, which we do with a transformer, we can drive a current in the plasma. And by producing that current in the plasma, we produce an additional magnetic field, which is a magnetic field that actually goes around in this direction as well, what we call a colloidal magnetic field. And so the combination of this toroidal magnetic field and the colloidal magnetic field gives you a spiral magnetic field. Magnetic field lines don't just run around the torus, but they spiral around the torus like this. There's that special spiraling configuration that we call a tokamak. So, basically you have the toroidal magnetic fields produced by the external magnetic field coils, these big coils here. You have the plasma current flowing around the torus, which produces a colloidal magnetic field. And the sum are this helical field line going around the torus and spiraling as it goes. That's what a tokamak is. And it turns out to be a very effective way of confining a plasma. And we've built some pretty big tokamaks. This one is JET, the Joint European Torus. It's a column in the UK. It's about 15 meters across, 12 meters high. It's produced temperatures of hundreds of millions of degrees. It's actually produced fusion powers of up to 16 megawatts. In fact, if you look inside JET, it's pretty impressive. This is now a cross-section through the donut, so you see the two halves of the donut here. This is what it looks like without a plasma in it. When it's being maintained. It's about 2 meters across here and about 4 meters high. And this is what it looks like when you've got a plasma inside it. And what's interesting is, plasma fills the chamber here. You can't actually see the plasma in the very core, because the plasma in the core is about 100 million degrees. And it radiates in a region of the spectrum that we can't see with our eyes. What you see here is actually the cold region around the edge of the plasma, where some of the plasma is interacting with the wall. This cold region So what does our tokamak look like? Well, ITER, which is what we're building here, is even bigger than JET. This structure is about 30 meters across and 30 meters high. This structure around the outside is what we call the cryostat. Keeps everything inside cold because we're using what are known as superconducting magnetic field coils. I'm not going to go into that. That's going to be the subject of a later lecture. Gary Johnson is going to talk about the tokamak. But it just gives you an idea of the impressive scale of what we're trying to achieve here. And inside this chamber, when we get it going, hopefully in about 10 years' time, we want to produce plasmas with temperatures in the region of 100 to 200 million degrees C. That's actually 10 times higher than the temperature in the center of the sun. And the reason it's so high is because the densities of the plasmas we can hold in a chamber like this are much lower than they are in the sun. So we have to have a higher temperature to make up for it, to make the reactions happen. And if we can achieve temperatures of 100 million degrees, then we can produce around 500 megawatts of fusion power. That's about 30 times the best fusion power being produced in jet. And we can do this for hundreds, even thousands of seconds once we learn how to control it all. And that's going to give us the basis then to design the next step after ITER, which should be a power plant which produces electricity. So that's a brief run through the basics of fusion. The message I want to take away is that fusion energy is produced by converting matter into energy. The fuel which we use to produce fusion energy is a mixture of deuterium and tritium, the heavy isotopes of hydrogen. To achieve fusion reactions, produce fusion energy, we have to achieve temperatures of around 100 million degrees. At such high temperatures, the fuel is a plasma. That is a mixture of positively and negatively charged particles. Because it's a mixture of positively and negatively charged particles, because it's a plasma, we can use magnetic fields to hold it all together. The tokamak, in particular, the ITER tokamak, is a special type of magnetic bottle for keeping the plasmas held together long enough and hot enough to produce fusion energy. And that's basically it in a nutshell. Thank you.